All right, so picking up where we left off, we want to minimize this error function, which is a function of m and b, the slope and y-intercept respectively of this line of best fit that we're trying to calculate a formula for. And so we want to minimize this thing. And again, this boils down to solving gradient E equal to 0. And of course, when I say 0, the gradient of E is a vector. And so when I say 0, I mean, 0, 0, the 0 vector. All right, so the gradient of E, let's go ahead and calculate this thing. This is the derivative of E with respect to m in the first component and the derivative of E with respect to b in the second component. So let's go ahead and figure out the derivative with respect to m. All right, so this is going to be the derivative with respect to m of this sum from 1 to n yi minus mxi plus b squared. All right, so this thing is basically just a fancy application of the chain rule. That's all this really is, right? It's a chain rule because m is stuck inside of some stuff that is being squared. All right, so this is really just a chain rule in disguise. So this thing is going to be, let's see here. Actually, before I do that, let me just look at what happens to an individual term, and then we'll add them all up later, okay? So the derivative with respect to m of yi minus mxi plus b quantity squared. All right, let's just look for any specific I. Let's see what happens here. So this is going to be 2, that's bringing the exponent down in front, taking the derivative of the outside, so to speak, times the inside left alone. And now I need to multiply this by the derivative of the inside with respect to m. And notice that that's the only place that m appears. So this is going to be the derivative of minus mxi with respect to m is just going to be minus xi. All right, so the derivative of E, the whole cumulative error function, meaning with the sigma inside of it, the sum in it, it's just going to be the sum of all these things, right? I'm just going to add all of these up, and that's going to be my derivative. So the partial of E with respect to m is the sum from 1 to n of 2 times negative xi times yi minus mxi plus b. All right, so there you have it. Very similarly, the derivative of the error function with respect to b, well, this is just going to be the sum from 1 to n. Right, I'm going to use the exact same logic I just used if I come back to maybe this line right here. Right, just imagine for a second that you're taking the derivative with respect to b instead. Well, the chain rule is initially going to give you the exact same thing, right? It's going to give you this part in front. And then the only thing that's going to be different is what happens to that right there. The derivative of negative b on the inside, that's just going to give you a negative 1 there instead of a negative xi. All right, so that's the only difference. So if I write that in down here, I'm going to have 2 times negative 1 times yi minus mxi plus b. All right, so those are my two derivatives, derivative with respect to m and with respect to b. So now, gradient E being equal to 0, is the same thing as saying that the sum from 1 to n of negative 2xi yi minus mxi plus b, and I equals 1 to n negative yi minus, negative 2yi minus mxi plus b. That whole thing should be equal to the 0 vector, 0, 0. Okay, so this looks awful, right? I think we can all take a second and appreciate that. This doesn't look good at all. However, it turns out to not be the worst thing in the world. All right, so let's just look line by line. Okay, so let's isolate the top line first. Top line looks like the sum I equals 1 to n of negative 2 times xi yi minus mxi plus b equals 0. All right, so the first thing I'm going to do, get the negative 2 out of there. You don't need that in there. Just divide it through, get rid of it. The next thing I'm going to do is distribute this xi to everything. And the last thing I'm going to do is actually remember what I'm trying to do in the first place here. I am trying to figure out, when all is said and done, I want a value of m and I want a value of b. Right? This is really what I'm after. I'm trying to figure out the values of m and the values of b that are going to make the gradient equal to 0. All right, so let's not lose the forest for the trees here. We want to isolate m and isolate b. Right? These are our main objectives. So get rid of the negative 2, distribute this thing. So what you're going to be left, distribute the xi. So what you're going to be left with, I'm also going to split this up into a bunch of sums with the ultimate goal being to isolate m and isolate b. So I'm going to have the sum from 1 to n, xi, yi. Right, that's those two terms right there. All right, then I'm going to have minus the sum from 1 to n. And here I'm going to have xi times mxi. So that's going to be, actually, let me rewrite this a little bit. Let me make it clear that the m is going to hop out in front. And now I have xi times xi, that's xi squared. And lastly, I have b times xi, so this is going to be minus b times the sum from 1 to n of xi. And that's all equal to 0. Okay then, what do we do with this? Right? So this is one line. Let's look at the other line and see if that gives us, you know, not necessarily better, but different information. All right, so let's look at this second line. The reason why I want to look at both of them first before deciding what to do is I want to see which of the two lines is going to make my life easier. All right, is one of them going to give me a more convenient formula or something to work with than the other? All right, so I don't want to just you know, go on autopilot at this point. I want to just take a second, take a breath, take a step back, and look at both of them, and then decide how to proceed. Okay, so I'm going to take this second line down here. So this is sum from 1 to n. Again, I'm just going to go ahead and cancel that negative 2 out. Since it's being set equal to 0, I can just divide it through. And what I'm left with is yi minus mxi plus b. That is equal to 0. Okay, So, again, I want to do the exact same thing I just did above. I want to split this thing up so that I can ultimately isolate M and isolate B. Or at least, get them as close to by themselves as I can. So the first thing I'm going to do here is distribute the sum to all of the different terms. And what do I have here? Minus B. And now this one is the only one that's a little bit strange. Oops, not I equals n. I equals 1 to n. This one's a little bit strange, right? When I factor this b out, it's really a b times 1, right? So I'm adding up 1 to itself n times when I do this distribution. In other words, this thing, right? What is 1 plus 1 plus 1 plus 1 n times? It's just n. All right, so I'll let you wrap your head around all this. I kind of zoomed through this this expansion, but make sure you follow this, right? Try to do this on your own without looking at what I just did, and make sure that you end up with the same thing. All right, so the idea here, if I go ahead and clean this up a little bit, the idea is that I have b times n right there. And now this is why I wanted to take a second and look at both the green formula right here and this blue formula right here side by side, because now I can try to decide, is one of them easier to work with than the other? And it's clear to me anyway that this blue one is the easier one to work with. All right, this formula is going to be the easier one to work with, explicitly because of that term right there. Right, if I compare that to what's going on in the green one, b is attached to a sum of n things. Here, b is only attached to the number of data points we have. That's what n is. It's the number of data points that we have. All right, so this is going to be nice for us. Let me take this onto the next page. So what I've got here is rewriting that second line. I've got the sum of my y's minus m times the sum of my x's is equal to bn if I add bn over to the other side, right? I'm just taking bn, adding it over. All right? So I end up with this. In other words, I know what b is supposed to be in terms of m. Right? B is supposed to be 1 over n, the sum of my y's minus m times 1 over n, the sum of my x's. And the reason why I've written it with the 1 over n's attached to the sums is because these things are means. Right? You're looking at, I suppose, what you'd call the sample mean of the yi's and the sample mean of the xi's. So, okay, so now we've got our slope, which is b. I'm sorry, our y-intercept, which is b, written in terms of all of our data points and our slope, which is m. So what we want to do, algebraically speaking, if I go back a page here, I want to take this formula and plug that value of b into it and see what we get. Alrighty, so this is b. I want to plug b into that crazy formula. So I've got my sum of the product of my data points minus m times the sum of the xi's squared. So that's going to be product of my data points minus m times the sum of the x's squared. And then I had minus b times the sum of the x's. So this is minus b times the sum over the x's. This is supposed to be equal to 0. All right, and what we want to do is just algebraically take this thing and plug it in for b. All right, so what this is going to give me, let me use this light blue color again. This is going to be, right, just expanding this part. This is going to be minus 1 over n sum of the yi's minus m 1 over n sum of the xi's. I equals 1 to n xi. And I'm going to multiply that by the sum over the xi's. All right? So this is what you end up with. You can solve for m from this. Right? We've got an m inside of that formula. We have the m over there. So you can go ahead and solve for m. And let's see what that's going to give us. So we are going to have, so this, let's see here, sorry, it's a lot to get your head wrapped around. So we've got a minus and a minus, that's a double negative, so that'll become positive. And we have to distribute this in as well, all right? So we've got sum from 1 to n xi yi minus m times the sum of the xi squared. And now I've got minus 1 over n. And here I've got the sum of my y's times the sum of my x's. Those are from 1 to n, of course, each. And then I have my double negative kicks in now. I've got plus m times 1 over n. And now I've got the sum of the x's squared, the whole sum squared, right? Okay, so this is all equal to 0. So now if I solve for m, I'm going to have m is equal to, so I need to isolate the stuff that doesn't have m in it, that's this and this. Move those over, so that's going to be my numerator. So this is going to be 1 over n I equals 1 to n of yi times sum from 1 to n xi, and then we're going to have minus the sum of xi yi, and our denominator is going to be all the stuff that was attached to m just a second ago. So we're going to have 1 over n times the sum squared of the xi's minus the sum of the xi squared. Right, so there is a formula for the slope of your line of best fit. It is not the most attractive formula I've ever seen in my life, but there it is. And the formula for b, of course, is somewhere. It's right here. And of course, you would have to plug that awful formula for m back into here to get a formula for b. All right, so there you have it. This would give you your line of best fit. At least best fit according to how we defined best fit in this context. Okay. So, let me know if any part of that didn't make sense. Hopefully it did. And I want to next make a video that addresses what would happen. Right, so say we've got our data that looks something like that. What happens if we look, instead of at this vertical variation, like we just were, right? This is what we were looking at just a second ago. Instead of looking at the vertical variation, what happens if we instead look at the shortest possible distance? All right, so what happens if we look at shortest straight line distance instead of shortest vertical distance? All right, what happens in that case? These little blue lines should look somewhat familiar to you. All right, so I want you to think about, what are these? What are they related to? All right. We've seen pictures like this a bunch of times in this class, just not in the context of statistics and linear regression. But we've seen pictures that look a lot like this. All right, so we've seen these before. Think about what those are before you watch the next video.